Hello, what if I tell you that two very common materials, iron and hydrogen peroxide, can together create one of the most powerful pollutant destruction systems known to environmental engineers? No expensive membrane, no sophisticated reactors, just iron, hydrogen peroxide, and some fascinating chemistry. Hello everyone, welcome to Clean Copper Talks. So this technology, known as the Fenton process, has been around for more than 130 years. Yet, it remains one of the most effective advanced oxidation processes used worldwide. Today, we will understand how the Fenton process works, why it is so powerful, its advantages, limitations, and where it can be applied across the globe. So stay till the last. At first glance, the Fenton process appears surprisingly simple. Iron is one of the most abundant metals on Earth. Hydrogen peroxide is commonly used as a disinfectant in households and hospitals. Individually, these substances are relatively ordinary. However, when they are combined together, appropriate conditions, they generate hydroxyl radicals. And hydroxyl radicals are among the strongest oxidizing species known in the environmental chemistry. The key reaction is Fe2 plus H2O2 gives Fe3 plus OH minus N hydroxyl radical. This reaction was discovered in the late 19th century by the British chemist Henry Fenton. Even after more than a century, this simple chemistry continues to play a major role in modern wastewater treatment technologies. What makes it special is that it produces radicals directly within the treatment reactor, allowing contaminants to be attacked immediately after radical generation. So, conventional wastewater treatment systems are excellent at removing biodegradable pollutants. However, they effectively reduce organic matter, suspended solid pathogens, and nutrients. However, today's wastewater contains contaminants that conventional systems were never designed to handle. Examples include pharmaceutical residues, antibiotics, industrial dyes, phenolic compounds, personal care products, and pesticides. Many of these chemicals are chemically stable and resistant to biological degradation. As a result, they persist in the environment for long periods. Their presence raises several environmental concerns. These compounds may cause ecotoxicity, endocrine, endocrine disruption, groundwater contamination, and development of antimicrobial resistance. To address these persistent contaminants, the researchers have begun exploring advanced oxidation processes. Among them, Fenton processes emerged as one of the most attractive options because it combines simplicity, effectiveness, and relatively low operational cost. Now let's understand the chemistry behind Fenton process. The primary reaction is Fe2 plus H2O2 gives Fe3 plus OH minus and hydroxyl radical. Here, ferrous ion reacts with hydrogen peroxide. Hydrogen peroxide acts as an oxidizing agent. Ferrous ion serves as a catalyst. This interaction generates hydroxyl radicals. These radicals possess an oxidation potential of about 2.8 volts. Hydroxyl radicals are highly reactive. They attack pollutant molecules through hydrogen abstraction, electron transfer, and addition reactions. The degradation process continues until contaminants are converted into carbon dioxide, water, and inorganic ions. But the chemistry does not stop here. Another important aspect of Fenton process is iron regeneration. Ferric ions can be reduced back into ferrous ion through secondary reaction. Because of this cyclic mechanism, the process can sustain oxidation for extended periods. This is one reason why Fenton chemistry remains highly efficient for treating recalcitrant pollutants. Operating conditions. Although Fenton process is simple, its efficiency strongly depends on operating conditions. One of the most critical parameters is pH. The optimum pH range is typically between 2.5 and 3. So why pH is so important? At higher pH values, iron tends to precipitate as iron oxide. This reduces the availability of dissolved iron for radical generation. At lower pH values, hydrogen peroxide becomes more stable and less reactive. Therefore, maintaining appropriate pH range is essential. Another important parameter is the dosage ratio between iron and hydrogen peroxide. Too little hydrogen peroxide means insufficient radical production. Too much hydrogen peroxide can actually reduce efficiency because excess peroxide scavenges hydroxyl radical. Reaction time also plays an important role. Most Fenton systems operate between 30 to 120 minutes. Temperature influences reaction kinetics as well. Higher temperature can accelerate reaction. However, excessive temperatures may lead to unnecessary decomposition of hydrogen peroxide. Therefore, optimizing these parameters is necessary for achieving maximum degradation efficiency. So what are the advantages and limitations? Like every technology, Fenton process has both strengths and challenges. The advantages it offers are it is relatively inexpensive, iron salts are cheap and readily available, hydrogen peroxide is commercially accessible. Second, the process exhibits rapid degradation kinetics. Many pollutants can be degraded within minutes. Third, implementation is relatively straightforward. Unlike membrane systems, Fenton treatment does not require highly sophisticated equipment. This makes it attractive for industries in developing countries. However, there are also limitations. One major drawback is sludge generation. As iron precipitates, iron-containing sludge is produced. Managing and disposing of this sludge can be costly. Another challenge is acidic operating pH. Wastewater often require acidification before treatment and neutralization afterwards. Chemical consumption is another concern. Hydrogen peroxide costs contribute significantly to operational expenses. Catalyst recovery can be challenging in conventional homogeneous Fenton system. Despite these limitations, Fenton technology remains widely used because of its advantages often outweigh its disadvantages. Applications in India. India presents several opportunities for Fenton technology. In Tirupur, one of the India's largest textile cluster, Fenton oxidation is used for color removal and COD reduction. Textile wastewater contains complex dye molecules that are difficult to biodegrade. The Fenton process offers an efficient treatment option. In Hyderabad, pharmaceutical industries are exploring Fenton-based systems for removing antibiotic residues. Reducing antibiotic discharge is becoming increasingly important due to concern about antimicrobial resistance. In Gujarat, chemical industries and common effluent treatment plant use advanced oxidation process for polishing refractory wastewater. Fenton treatment is also applicable in pesticide manufacturing industries where persistent compounds require strong oxidation technologies. As regulations become stricter, Fenton chemistry is expected to gain even wider acceptance in India. Recent advances in Fenton technology. Researchers are continuously improving Fenton chemistry. One emerging area is nano-Fenton technology. Nanoparticles provide large surface areas and enhanced catalytic activity. Heterogeneous Fenton systems are another exciting development. Instead of dissolved iron, solid catalysts are employed. This approach reduces sludge generation and facilitates catalyst recovery. Magnetic catalysts are attracting considerable attention. Materials such as magnetic nanoparticles can be easily separated using external magnetic fields. Photophantom technology combines light irradiation with Fenton chemistry. Additional hydroxyl radicals are produced, significantly increasing degradation efficiency. Artificial intelligence is also emerging in the field. Artificial intelligence is also entering the field. Machine learning algorithms are helping scientists optimize operating conditions, predict treatment efficiency, and design next generation catalysts. These innovations may define the future of advanced oxidation technologies. So, as a conclusion, more than 130 years after its discovery, the Fenton process continues to remain one of the most important advanced oxidation processes. Its chemistry is simple, its oxidizing power is extraordinary, and its industrial applicability has already been demonstrated worldwide. Although challenges such as sludge generation and chemical consumption remain, ongoing innovations are steadily addressing these issues. The Fenton process has inspired several modern technologies include photofenton, electrofenton, nanofenton, and heterogeneous fenton systems. Can technology discovered in 19th century still solve 21st century water problems? The Fenton process suggests that the answer is yes. In our next video, we will discuss photofenton process and discover how sunlight can make wastewater treatment more efficient. If you enjoyed this video, don't forget to like, share and subscribe to Clean Copper Talks. Thanks for watching and I will see you in next video. Till then, tata, bye bye, take care.